Hello, my dear students, and welcome to a new chapter, or maybe actually it's not a chapter, it's a new short lecture related to our wireless sensor network course, typically self-powered sensor nodes. In the previous chapters along the module, we have discussed together a series of constructing blocks to construct a wireless sensor node, considering a sensor itself, an interfacing circuit, an energy harvester, a dcdc converter for energy management, and a lot of stuff. Now, what we are going to do today is we are going to explore together the possibility of integrating a complete node. I can understand that we are still missing some blocks in our complete node, like, for example, the data processing units and also the wireless communication links. But let's start to demonstrate, or let's start to implement what we already have discussed in the previous sections of the course. So for this example, or for this lecture, I will consider an example related to a photodiode detector, or in other words, a light sensor. So let me start showing my presentational slides here. Okay, so this is the sensor I'm going to consider during this lecture. So it's a photodiode to absorb light or collect light. Then we have an RB, or a base resistance, and a metal resistance, a bipolar junction transistor, and a VCC terminal. Okay, so before start in exploring the details of this sensor as well as all the adjacent blocks, let's start with a general description of a system. How we are considering a sensing node. So we can say that our sensing node in general consists of a sensor that senses some phenomena, which is light for this example. And this sensor is then connected to what's called a sensor interface circuit, which should act to make the system or the input voltage from the sensor compatible with the next unit, which is most likely an ADC, or energy digital converter. And then we have our communication link, whatever RF or whatever. And to power this sensor, as well as to power this interfacing circuit, we should consider here the supplying power will come from an energy harvester, and in between we have our dcdc converter. So this is a general out view for the process itself. In this model, we are going to consider the sensor, the interfacing circuit, the energy harvesting unit, and the dc-dc converter in order to make an integrated node to combine all these stuff together. So let's start doing this process together. And let's start with the sensor itself. So our first start is the sensor. So our sensor, as we just demonstrated, is something like that. This is a bipolar junction transistor. The emitter is connected with a resistance called RE to the ground. And the base is connected to a resistance called RB, again to the ground. And here we have our photodiode. This is our photodiode, which should convert the light into current, as we will see. And this is I'm sorry, no, this is wrong. This is the output. And of course, this is VCE. So this is VCE, and this is VP. Okay, so let's start to analyze this circuit together. And let's start with the most critical point in this circuit, which is the photodiode itself. I think we already have studied together in the first chapter when we consider light sensors. We studied the photodiode phenomena, or how a p-n junction can act as a photodiode. And in this, we have recognized a very important observation related that in photodiodes, in light sensors, current is conducted as a reverse or in the reverse direction. That's why you find here our photodiode is connected in a reverse direction in terms of a forward junction, because basically the voltage here is greater than the voltage here. The voltage here is VCC, and the voltage here is definitely below VCC, because simply VCC is the highest voltage in the circuit. So the current is moving, or the current direction is in the reverse direction, and that's why this photodiode acts. Another important information related to the light harvesting or the light sensing phenomena is that the light irradiance is directly proportional to the current flowing in the diode in the reverse direction. So the higher the current irradiance, the higher the I photon. So I photon is typically the current moving here. This is I photon. So how we can use this to make an analysis? Again, if you remember, my dear students, usually I told you that whenever you consider a sensor, the basic point is to make a relation between the input and the output. So from this analysis, we can understand that our input is this I photon, which is directly proportional to the irradiance. So the output is this voltage, which is the voltage connected to the emitter of the BGT. How we can make this link between the input and the output? You can understand that here, the main linking term is this VPE voltage, because the current moving here will definitely affect this point, which is VP, and the emitter voltage here represents the output voltage. So let's start with the base side. If you make a nodal analysis here, my dear students, you will find that this I photon, or the current flowing in the photodetector, will going to be branched. Some of these current will move here, which we call the I base, or the current moving in the base, and the other current will move here, which is IRB, or the current moving in the resistance RB. But from our previous electronic classes, you remember that whenever we have beta high, or considering high beta, we can say that IB is very, very, very small. Or in other words, you can say that IB is much smaller than IRB. Herein, you can make a very simple approximation saying that I photon is approximately equals to RRP. So the current flowing in this resistance is nearly the same as the current flowing in the photodetector, assuming that no current is flowing in this base branch. So in this context, you know the current flowing in the resistance, and you know that this is a ground terminal. So basically now the VB, or the voltage applied to the base, equals to I photon times RB. So the higher the irradiance, the higher the I photon, the higher the VP. But please don't forget that to keep your transistor, this BGT transistor, to keep this BGT transistor on, you have to have a VPE equals to 0.7. So VPE should remain equals to 0.7 to keep this transistor on. So what is VPE? VPE is the voltage on the base, which is typically I photons times RP, and VE is the voltage on the emitter, which is exactly the output voltage. So now we can write an equation saying that VPE equals VP minus VE equals 0.7. I'm sorry. I think this is now correct. Okay, so VP is I photon times RP. And VE is typically the output voltage. And this is 0.7. So you can say, my dear students, that V output equals I photon times RP minus 0.7. And this will be your transfer function linking the output, the input current, which is I photon, which is directly proportional to the radius, to the output voltage here. Now you can start to plot this relation, considering this is I photon, which is the input, and this is V out, the output voltage. Plotting this relation will give that when I photon is equals to 0, you will get the output equals to negative 0.7. Then you have a linear relation like that, where the slope of this relation is typically RP. And this intersection point will be, by putting V output equals to 0, will be by putting, yes, V output equals to 0 will be 0.7 over R. Now you can understand, my dear students, from our previous lecture that your sensitivity is a concrete function in RP. So you can control it, because if you remember, the sensitivity is a relation between the input and the output. So you can control your sensitivity by controlling this RB. We will calculate it later on. So this is a transfer function connecting the output with the input, and this is a straight line, or a linear relation between the output and the input of this stage. Okay, so this is our first requirement, to get a relation between the input and the output, and to get that transfer function, and to know how we can control the sensitivity. So here the sensitivity is directly controlled by this RB. So a next point will, in order to proceed with our design, we have to explore a lot of unknowns in this circuit. So for example, we don't know what is VCC. We don't know what is RP, what is RE. We don't know anything about them. So we should start making our design more clear to get or to capture these values. Usually in electronic design, you have to start with assumption and then complete to calculate other terminals and to check if your assumption is correct or not. Basically speaking, VCC should be a positive voltage. Again, this is to force this die to be in a reverse bias. So the voltage here is greater than voltage here. So this should be a positive voltage. So let me, for example, say, that assume VCC equals 3 volts. Okay, if we assume VCC equals 3 voltage, then what will be our next action accordingly? Okay, let's see. Now we assume this VCC is a 3 voltage. So we can get, we still need some more assumptions actually to proceed, but let's see here, start to think about that. When this VCC equals 3 voltage, that basically means that we have here a VCE parameter. This VCE parameter, if you remember, is a very critical parameter in a MOSFET. Why? Sorry, in a BGT. Why? Let me remind you of that. If you remember the IV curve, for a BGT. So for the IV curve for a BGT, usually we are forcing our BGT to work in what we call here the active region. In this active region, my dear students, we have a VCE varying because this axis typically represents the VCE. A minimum value for the VCE, this point, we call it, if you remember, VCE sat. So this is the minimum value for a transistor to work in the active region. If VCE is lower, then you transfer automatically to what's called the saturation region. So your minimum VCE is VCE sat. VCE sat represents your minimum VCE. So what is VCE based on this graph? VCE is VCC minus, VC minus VE. VC is directly connected to VCC, and VE is directly connected to the output. So you can say that your VCE equals to VCC minus V output. So how can we get a minimum VCE? Typically, when V output is maximum, due to this minus sign. VCC is constant. VCC will not change. So you will get VCE minimum when you get V output maximum. So when this VCE is minimum, that will lead to what's called a V output maximum. So now you can pick up the V output maximum because simply, you know, this VCE sat minimum or VCE sat actually is 0.2, and this VCC, you assume it's 3. So now you can get V out max, which will be 2.8 voltage. So you know this V output max, which will be the we call it the maximum swing, or the upper limit of your voltage your output voltage. Perfectly. So we get this point. So this point represents the maximum voltage. So if we return back to this, yes, are you letting me pick it up? I think, yeah. Yes, this one. So if we return back to this graph, we will find that based on what we just calculate, that this point reflects the 2.8 voltage. So your output voltage will swing between negative 0.7 and 2.8 voltage based on your input. So if you don't have any light, I mean, if the I photon is equal to 0, you will get negative 0.7. If you get the maximum acceptable light to be taken, then you will get a voltage of 2.8. So again, let's still work operating on this point, on this maximum point. So when the current is maximum, then you have a 2.8 voltage. So, you know, you have this equation, but unfortunately, you still have more unknowns because you know the output, a maximum V output, but you still have two unknowns, which is I photon and RP. So to calculate one of these two outputs, you have, or one of these two unknowns, you have to assume one of them. Here, let's assume an I photon maximum of 200 milliampere. So when this I photon is maximum, which is 200 milliampere, then you will have a V out maximum of 2.8 voltage. Now you can return back to this equation. So at 2.8 operating voltage, your current is 200 milliampere. So you can get here, you can say that, okay, so V out equal I photon RP minus 0.7. So, you know, V out is at its maximum is 2.8 equals I photon, which is 200 milliampere or 0.2 ampere, RP minus 0.7 or 0.2 RP equals 3.5, or RP equals 3.5 times 5. So 5 times 5, 5 times 3, this is, I think this is 15 plus, it will be, I think, 17.5. Okay, so this is RP. So now you get RP. So so far, we know I photon maximum, V output maximum, VCC, RP. We are still only have one only parameter, which is still unknown, which is RE, if you go to this. So as I just mentioned, so the current flowing here is typically V output over RE. So as I just mentioned, we assume that the maximum current is 200 milliampere. So let's keep this assumption in both branches. So I will say that assume again IE maximum equals 200 milliampere. So RE equals the output voltage is 2.8 over 0.2. This will result by, so this is 10 and this 504. I think it will be something like a 14 ohm resistance or something like that. Sorry, I don't have a calculator right now, so maybe I make some errors. So this is the values for RE and RP and all these circuits. And I think we now make a full analysis for the circuit with all the inputs and the outputs and all these considerations, which is still, I think, what we need so far. Okay, so before leaving this sensor, I think we still need one more information, and this is a basic information to move to our next block. Let me go to, this block. So as I just mentioned, this sensor will be operated using an energy harvester to a dc-dc converter. So to make this matching, or what we call the bar budget or the energy budget, we have to have we have to know the operating power of this sensor. So what is the operating power of this sensor? It's very straightforward. The operating power of a sensor is mainly the power driven from the supply. Here we have a single supply, which is 3 voltage. This supply have two current branches. The first current is I photon, and the second current is IC, which is typically equal IE because we assume a high beta. As I just mentioned, the maximum I photon is 200 milliampere. The maximum IE is 200 milliampere. This is my design assumption. So what I can say simply is the power dissipated in this sensor is equals to the 3 voltage times 200 plus 200, which is 400 milliampere or 0.4 voltage. So this is 40% of the 3 voltage. So it will be, so I think this 10% is 0.3. So so we have here 0.3 times 4. So I think this will be 1.2 watts. Okay. So the power dissipated in this sensor is 1.2 watts. So now it's time to pick up an energy harvester. We already agreed from the previous lecture, if you remember, when we consider energy harvesters, that we are not going to go into the details of energy harvesters. As I mentioned in the previous lecture, we already have a separated course related to energy harvester system where you can explore more and more details about how to build an energy harvester. So in this design problems, we are considering energy harvesters as just a black box. And what you are searching about is what's called the power density of your energy harvester. So let me assume that, for example, I'm going to use an outdoor energy harvester. So my energy harvester will produce a power. So the power for the harvester is 100 milliwatt per centimeter square. So in order to provide or to match this 100 milliwatt per centimeter square with the 1.2 watt, typically here I need 12 centimeters square. So if I multiply this 12 centimeters square times 100, I will get 1.2 milliwatts, or 1.2 watts, sorry. But as we agreed together, here I'm assuming a full matching between my energy harvester and my sensor, which is relatively not realistic somehow, because circuits are associated with losses. I need a DC-DC converter, which we will consider in few seconds. So this DC-DC converter is not 100% ideal power balance block. Accordingly, we have to assume some sort of power losses. So in this case, I will consider 15 centimeter, for example, 15 centimeter square area. So 15 centimeter, which is, for example, 5 centimeter times 3 centimeter area. So this 15 centimeter area will give around 1.5 watts. So I will harvest 1.5 watts to use 1.2 watt. Now I'm assuming about 80% efficiency, which is 1.2 over 1.5 is typically 80%. So this is 80% efficiency. So I'm considering as if my DC-DC converter is working with an 80% efficiency. By the way, this is a very realistic number when you consider a low power DC-DC converter for IoT application. This is a usual number for a DC-DC converter. So now I decide to have an energy harvester, a direct light energy harvester, or outdoor energy harvester, which will give 100 milliwatt per centimeter square as a power density. I will use 15 centimeter square area. Then I will pick up 1.5 watts with 80% efficiency to operate the 1.2 watt sensor. One step remaining, which is the operating voltage and current. So let me assume that this 100 watt is going to operate with 4.8 voltage. Okay, so now your DC-DC, your energy harvester is producing 4.8 voltage, but your circuit here only needs 3 voltage to be operated. So what you are going to do, simply to do is you are going to use a DC-DC converter. So what will be the characteristics of the DC-DC converter? In terms of input, we have an input of 4.8 voltage. And we need to buck this voltage, to be 3 voltage. So here, using the steady state equation, you can say that V out equals D times Vm, knowing that this is 3 and this is 4.8. Then you can calculate D. I think it will be 3 over 4.8. So I think it will be 0.625. I think. Again, I'm sorry if I make any calculation mistakes because I'm just using my head to calculate. So this is the duty cycle for our harvester, and as you know, as far as you are bucking the voltage, so you are going to boost the current. Please remember that you need here 400 milliampere. I'm sorry. So you have to boost this 400. So this is typically to calculate IN will be. This should be boosted, so it's 0.4 ampere over 0.625. Have to I'm sorry. So IN is 0.4 times 0.625. So this will be I think around 0.25 maybe, 0.25 milliampere or 250 milliampere. So you have to have a 250 milliampere as an input with 4.8 voltage to get 3 voltage in the output with 400 milliampere in the output stage. So this is for the DC-DC converter. So now you know the DC-DC converter, you know the energy harvester as a source in terms of power density, you know the sensor itself. So back to the basic block. So we consider the sensor itself, we consider the DC-DC converter, we consider the energy harvester, we just remaining the interfacing circuit. So what is the interfacing circuit? The interfacing circuit is the analog interfacing circuit that should act to convert the output range of a sensor into an adaptable range to be inputted to the DC-DC converter, so to the ADC, analog to digital converter. So let's assume, based on the example we do together in the class, let's assume that we need an ADC or analog to digital converter with 0 to 15 voltage. So this is the input needed for the ADC. Let's say so. To reach this input, so basically, this should be the output for your interfacing circuit. So your sensor interfacing circuit should have an output from 0 to 15. And here we are considering the input now. So what is the input? We already know the input. If we return back here, let me pick up the correct page. Yes, okay. So this one. So we have that. We know the swing of the input. So our sensor will produce an output voltage that ranges from negative 0.7 to 2.8 voltage, as we already discussed in the transfer function here. So the input for this interface circuit will vary from negative 0.7 to 2.8. So basically, the function of this sensor interfacing circuit is to convert the negative 0.7, 2.8 range to the 0.15 range. How we can make this? Okay, basically, as you can see, we need two functions actually. First, we need to shift this range to be fully positive range. So you need to shift this negative 0.7, 2.8 to be 0, 3.5. Simply by making a positive offset of 0.7. So if we shift this by 0.7, you will shift the, or you DC offset that. Then you need to amplify this 0.35 to be 0.50. So it is considered as we are doing two tasks, two cascaded tasks. So what you are going to do, as we agreed, once you are outputted from a sensor, you should consider first a buffer stage. So when this is the V out from the sensor, which is negative 0.7 to 2.8. This value, sorry, yeah, this is true. So this value will be inputted to a buffer stage here. So that's an isolation stage. Then what will happen is I need to make this biasing 0.7 volts. We have a series of techniques to do so. Maybe you can use a summer and a summer operational amplifier to sum 0.7 to your input voltage. So this is a very basic circuit like that. This R and R, and here I will put the positive 0.7, and here I will insert it like that. And I should have a feedback resistance like that. Okay, so this is a summer or an adder. I think if you go to your electronic classes, you will definitely remember this circuit, which adds two voltages. So you will add your input plus 0.7. Here, the adding ratio is typically equals to 1 because all resistance are identically the same. So you are not doing any weighted adding or weighted summing process. So you are going to add all these stuff together to get this plus 0.7. So this terminal is then need to be amplified. So I'm going to use a very standard amplifier. So if I put this 15, sorry, and this 3.5, then the amplification ratio will be 15 over 3.5, which is typically the same ratio I need. And finally, I will terminate with another buffering stage to make an isolation to that. So this is how we can manage an interface circuit, a very simple interface circuit, in order first to bias or offset your voltage with an positive 0.7, then amplify your voltage with the needed ratio, and then you get the output voltage for so this is a very valid example to make a complete sensing node using these different elements, combining these elements together to form a node. No, so now we cover the sensor itself. We cover the energy harvester, the dcdc converter. We cover the also we cover the interfacing circuit, as you can see. So this is a valid or a complete example for a node. As I just mentioned, we didn't consider yet the communication link. Maybe this is a part of the next lecture or whatever. So maybe this will be what is after the ADC or the analog digital converter, how I'm going to process the data and how I'm going to deliver to this data to a central node. But for the analog part of a node, I think this completes the analog part of a node, either in the form of the sensing and the sensor interfacing circuit, or in the form of energy harvesting and energy management circuits. Thank you very much, my dear students, for this for your concentration. I'm looking forward for our next lecture, inshallah. Thank you very much.